Okay, we've got a problem where there's a wheel. And it has a radius. We're not giving numbers here. The radius is capital R. And it has a moment of inertia that's given as I. Now, I use I sub wheel because we're going to have other moments of inertia. And then we put a mass on this wheel at a place where it's close to but not at the low point. Well, I'm going to make the mass over here. We could make it closer to the low point, but I want to leave myself room to label sketches and so forth. So I'm going to put it over here a ways. Okay, so here's the mass. So we're going to say this is our mass, M. And we're going to then ask if the mass is put on here with the wheel stationary, how does the wheel move? Okay, and ultimately we want the equation of motion starting from rest. So, first thing I asked people to do was, well, sketch me whatever it is that causes this thing to move. Okay, represent that entity, whatever it is that makes this thing move. Because it's stationary, how did putting a mass here cause it to move? Well, people were pretty good about sketching a force vector, which I'll label mg. The mg vector, the weight vector, the force exerted by gravity. Okay? Now, the wheel is said to be balanced, so there are plenty of other forces around, but there's nothing else that exerts a net force on this system at all. Okay? Now, well, okay, that's great, but what kind of motion is this thing going to go through? Well, the wheel, okay, motion is created by the force mg. Okay? Now, of course, the force mg won't make any motion happen if the mass happens to be directly below the axis because of the symmetry of the wheel. It's been stated. So I'll go at the said point. And this point, we give a name. This is, let's see, what are we going to label here and how do I'll label the point here and just use an arrow to indicate, okay, there it is. Okay, the mass is at point P. P is not at the low point, but it's not far from the low point, so it's not at the high point either. And if it's any point but the high point or the low point, it is going to cause motion. We also have the idea that this is frictionless, okay? So I said negligible friction. I don't want to write out that whole word, so I'm going to just say no friction. Okay, so motion's created by mg at this point. Equation of motion, we want the equation of motion from rest. Okay, what kind of motion are we going to have? The mass is on the inside of the wheel, and we say it clings to the wheel. Okay, it's going to stay at the same point on the rim of the wheel. So what kind of motion are we going to get? Well, motion will be rotational. So we model angular motion. And that's going to give us I'm wanting to say theta of t, but I've chosen not to use theta here. So we'll see what that gives us when we do a little more labeling, okay? So, what is it that causes this thing to move? Okay, well, angular motion in the first place, if nothing is speeding this wheel up or slowing it down, it's just going to continue rotating at constant velocity because these are the only forces involved. Nothing's going to change. Okay, well, the angular motion is changed by angular acceleration alpha. And what is it that causes alpha to change? Well, it's a torque, as we should know. Alpha equals torque over moment of inertia. Just as for linear acceleration, the acceleration is equal to the net force divided by the mass of the object being accelerated. When we move to angular motion, we have angular acceleration. Instead of net force, we're going to talk about net torque, and I should have put a net on this. Can't read it, it's there now. Okay, and moment of inertia takes the place of mass. Now we need to understand the details of why those things happen, but that is the set of relationships. So now the key is the torque. And the torque is a vector. Okay. What's the torque? How are we going to get the torque in this situation? Well, we know that this is the only, this is the net force acting on the system, and depending on where that net force is applied, it's going to create a torque, isn't it? Okay, so the torque is what? Well, okay, torque equals R cross L, where R is what? R is the vector from the axis of rotation to the point of application. And as it turns out, that could be the vector from the center to any point on the line of action of the force. And we've seen why that's true, whether we're completely aware of it right now or not. We're going to actually apply that in a minute. But I'm just going to use the whole R vector in the mg vector. Okay, so R cross mg, and we could depict those two vectors. Well, R cross mg, fingers in the direction of R, turn toward mg, our thumb is pointing into the board. So the torque is in the direction into the board. And it depends on the angle between these two vectors, because wherever this mass is on the rim of the wheel is going to be at the same distance big R from the axis, right? Because it's moving in a circle. And the mg is going to be vertically downward, so that as the wheel rotates, the angle between the R vector and the mg vector will change. So I'm going to define the angle, and I'm actually going to end up modeling this in terms of the angle, because R and mg are always the same, but the cross product also depends on the angle. So the only thing that's changing in this cross product will be the angle. As the wheel rotates, only this angle is going to change. Magnitude of this vector and magnitude of this vector are always going to be the same. So I'm going to use an angle here, and I'm not going to call it theta, although we could. Okay, I'm going to call that angle beta. I don't want to use theta because of the connotation I still want people to get used to, where you put an x-axis and a y-axis in this thing, and theta is the angle as measured from the positive x-axis in the counterclockwise direction, so that you can apply the circular definitions of the sine and cosine function. And that's kind of actually important when you're dealing with rotation. It's important to be able to do that. Now I could, my x-axis doesn't have to go this way. It could go this way. And my y-axis could go this way. Okay, and if you want to model it that way, that's great. Then you could call this angle theta without any ambiguity, and everything would work out. I didn't want to confuse the issue by putting the coordinate system in that weird of an orientation, although we've used the coordinate system in other notation, in other orientations when we're dealing with an inclined plane and so forth. Okay, well, anyhow, there it is. You get your mg vector, your r vector, and your beta. And applying the definition of torque, and I'll discuss that a little more in detail, we find that the magnitude of the torque, and I'll put an absolute value sign around that, is the magnitude of the r vector times the magnitude of the f vector times the sine of the angle between them, the sine of the angle beta. That means that the magnitude of the angular acceleration is going to be the magnitude of r times the magnitude of your force times the sine of beta over the moment of inertia. And of course, the magnitude of r is just big R. The magnitude of f is just mg. Beta is what it is. Okay, so here we have an expression of the magnitude of the acceleration. We still have to deal with the direction of the acceleration, and we're going to take care of that by measuring beta counterclockwise from the downward vertical direction. Okay, the angle from the downward vertical out to the r vector, so that when beta, or when the wheel is, I think it's clear that we understand that the wheel is going to come through the equilibrium position and come over here, right? Or the mass will end up on the left of the equilibrium position, then it'll rotate back and forth. In that case, beta, as measured in the counterclockwise direction, will all of a sudden become clockwise, meaning it'll become negative. And that will change the sign, SIGN, of the sine function to negative. And when we put all that together, we're going to find that we have the conditions of simple harmonic motion in the simple harmonic angular motion. So we're going to continue to develop this.